What if I told you that gravity is not pulling you down right now? What if the force you have felt your entire life, the one keeping your feet planted on the ground, is not really a force at all? This might sound absurd. After all, we drop something and it falls. We jump and we come back down. Surely something is pulling us, right? But here is the truth that will change how you see the universe forever. Gravity is not a force. It never was. For centuries we believed Isaac Newton when he told us that gravity was a pulling force between masses. An apple falls because Earth pulls it. The moon orbits because Earth pulls it. Simple, elegant, and completely wrong. Well, not completely wrong, but fundamentally incomplete. Newton gave us a description of what gravity does, but he never explained what gravity actually is. That explanation would come much later, from a man who looked at the universe in a way no one had before. In 1915, Albert Einstein published his theory of general relativity, and with it, he shattered our understanding of reality itself. Einstein revealed something extraordinary. Gravity is not a force acting between objects. Gravity emerges from the curvature of space and time. Yes, you read that correctly. Space and time, the very fabric of our universe, can bend and warp. And when they do, everything changes. Think about space for a moment. Not outer space, but the space around you. The emptiness between objects. We tend to think of it as nothing, just a void where things happen to exist. But space is not nothing. Space is something. It is a physical entity that can be stretched, compressed, and curved. Now, add time to this picture. Time is not just a clock ticking in the background. Time is woven together with space into a single entity called space-time. This four-dimensional fabric is the stage on which everything in the universe performs. Now here is where it gets interesting. Mass and energy warp the fabric of space-time. Imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a depression, a curve in the sheet. This is what massive objects do to space-time. They bend it. Earth, with all its mass, warps the space-time around it. The Sun, vastly more massive, warps it even more dramatically. In fact, every object with mass or energy does this. Even you. Even the phone in your hand. Even the smallest atom warps space-time, though the effect is so tiny, we would never notice it. But massive objects? They warp space-time dramatically, creating deep curves that dictate how everything around them moves. And here is the revelation. Objects do not move because some invisible force is pulling them. They move because space-time tells them how to move. When you drop a ball, it is not being pulled down by Earth. Instead, the ball is moving along the curved space-time that Earth has created. The ball is simply following the geometry of the universe. It travels along what physicists call a geodesic, which is the shortest path through curved space-time. In flat, uncurved space, a geodesic would be a straight line, but in curved space-time, geodesics curve. So objects appear to accelerate toward massive bodies, not because they are being pulled, but because the very space they exist in is curved. This is not just a philosophical distinction. This is a complete reimagining of how the universe operates. Gravity explains motion without any direct contact between objects. There is no mysterious force reaching across the void. There is only geometry. The universe behaves like a geometric system where the presence of mass and energy determines the shape of spacetime, and the shape of spacetime determines how objects move. But if gravity is just curved spacetime, then why does it affect everything equally? Why does a feather and a hammer fall at the same rate in a vacuum? Because spacetime curvature does not care what you are made of. It does not matter if you are light or heavy, dense or diffuse. You follow the same curved path through space-time. This is why astronauts on the International Space Station feel weightless. They are not beyond Earth's gravity. Earth is still curving space-time around them. But they, along with the station, are in free fall, following the same geodesic path through curved space-time. Now, here is something that will make you wonder even more. Light is affected by gravity, even though light has no rest mass. How is that possible? If gravity were simply a pulling force between masses, light should sail right through, unaffected. But it does not. Light bends around massive objects. It follows the curves of spacetime just like everything else. This happens because gravity acts universally on energy and momentum, not just on mass. Light carries energy, light carries momentum, and spacetime curvature responds to that. This realization opens a door to one of the most stunning phenomena in the cosmos. If light bends around massive objects, then those objects can act like lenses, bending and focusing light from distant sources. Galaxies can magnify other galaxies. Stars can warp the images of stars behind them. Black holes can twist light into rings. The universe becomes a hall of mirrors, where nothing is quite where it appears to be. But before we dive into that visual spectacle, we need to answer a question that might be nagging at you. If light has no mass, why does it bend at all? What exactly is happening when a photon, a particle of pure energy, travels past a star or a galaxy? The answer lies in understanding what light truly is and how it interacts with the geometry of spacetime itself. And that is where we go next. We left off with a puzzle that seems to defy logic. Light bends around massive objects even though light has no mass. This should not make sense. If gravity were truly a force that pulls on mass, then massless light should sail straight through the universe, unaffected by anything. Yet we observe light curving around stars, bending around galaxies, and even spiraling into black holes. How is this possible? The answer reveals something profound about the nature of light itself and the geometry of our universe. Let us start with what light actually is. A photon, the fundamental particle of light, has zero rest mass. If you could somehow catch a photon and place it on a scale, it would register nothing. Zero. This is not because our scales are not sensitive enough. It is because photons genuinely have no mass when at rest. But here is the crucial detail. Photons are never at rest. They travel at the speed of light, always, without exception. And while moving, light carries something incredibly important: energy and momentum. Energy is not the same as mass, but Einstein showed us they are intimately related through his famous equation, relating energy to mass and the speed of light squared. Mass can be converted into energy. Energy can manifest as mass. They are two sides of the same coin. When light travels through space, it carries electromagnetic energy. This energy is real, measurable, and powerful. The sunlight warming your skin right now is pure electromagnetic energy delivered by countless photons streaming through space. But light also carries momentum, which might seem strange for something with no mass. We normally think of momentum as mass times velocity. How can something with zero mass have momentum? The answer lies in quantum mechanics and relativity working together. Light has momentum proportional to its energy divided by the speed of light. This momentum is why light can push objects, create pressure, and transfer force. Spacecraft have even been designed with solar sails that are pushed by the momentum of sunlight. Now here is where everything connects to gravity. General relativity tells us that space-time curvature responds to energy and momentum, not just mass. When Einstein wrote his field equations, the source of gravity on the right side of the equation is not simply mass. It is the stress-energy tensor, a mathematical object that encodes all forms of energy, momentum, pressure, and stress in space-time. Mass is just one component of this tensor. Energy contributes, momentum contributes. Even pressure contributes to the curvature of space-time. This means that light, despite having zero rest mass, affects space-time because it carries energy and momentum. A beam of light creates its own tiny curvature in space-time. Now, the curvature from ordinary light is absurdly small, far too weak to detect with any current technology. But theoretically, if you concentrated enough light energy in one place, you could create significant space-time curvature. Some physicists have even speculated about creating microscopic black holes from pure electromagnetic energy, though this remains entirely theoretical. More importantly for our story, light is affected by space-time curvature created by massive objects. This is the key insight. Light does not bend because massive objects pull on it. Light bends because it follows the geometry of space-time, and that geometry has been curved by mass and energy. Think back to our trampoline analogy. The The bowling ball creates a depression in the fabric. Now imagine rolling a marble across the trampoline. The marble follows the curved surface. It is not being pulled toward the bowling ball by some force. It simply follows the geometry of the surface it travels on. Light does exactly the same thing in four-dimensional space-time. A photon travels through space, always moving at constant speed. This is a fundamental law of physics. The speed of light in vacuum never changes. It cannot slow down. It cannot speed up. Every photon, whether it came from a flashlight or from a star billions of light years away, travels at exactly the same speed, approximately 300 million meters per second. But while light cannot change its speed, its direction can change. When light encounters curved space-time, the path it follows curves with that geometry. Light always takes what physicists call a null geodesic, which is the path that light must follow through space-time. The word null refers to the fact that, from the photon's perspective, it travels zero distance in space-time. This sounds bizarre, but it is a consequence of traveling at the speed of light. Time dilation becomes so extreme that from the photon's frame of reference, no time passes during its journey. Geodesics are the shortest paths through curved space-time, or more precisely, the paths of extremal length. In flat, uncurved space-time, geodesics are perfectly straight lines. This is why light travels in straight lines through empty space far from any massive objects. But straight lines only exist in flat space. The moment space-time curves, geodesics curve with it. Light must follow these curved paths. It has no choice. The geometry of space-time dictates where light goes. Think about what this means. When light from a distant star passes near our sun, the space-time around the sun is curved. The light follows that curvature. From our perspective on Earth, the star appears slightly displaced from its true position. During a total solar eclipse in 1919, astronomers measured exactly this effect. Stars near the sun appeared shifted by precisely the amount Einstein's equations predicted. This observation made Einstein world famous and confirmed that space-time really does curve. The bending of light is entirely geometric, not force-based. There is no gravitational force reaching out and tugging on photons. There is only the shape of space-time, and light following that shape. This distinction might seem subtle, but it is revolutionary. It means gravity is not one of the fundamental forces of nature in the way electromagnetism or the strong nuclear force are. Gravity is geometry. It is the curvature of the stage on which everything performs, and this geometric nature of light bending leads to extraordinary consequences. If massive objects curve space-time and light follows that curvature, then massive objects can act like lenses. Just as a glass lens bends light rays to focus them, a massive galaxy or star can bend light from objects behind it. This is not just a theoretical possibility. We observe it constantly throughout the universe. Galaxies bend light from more distant galaxies. Galaxy clusters act as cosmic magnifying glasses. Even individual stars can lens the light from stars behind them. This phenomenon has a name, gravitational lensing, and it is about to become one of the most powerful tools we have for exploring the universe. Because when light bends around massive objects, it does not just create pretty pictures. It reveals what is truly out there. It maps the distribution of matter in space. It shows us structures we could never see otherwise. And most remarkably, it exposes something invisible, something that makes up most of the mass in the universe, but emits no light whatsoever. Now that we understand how light bends around massive objects by following curved space-time, we can explore one of the most visually stunning and scientifically powerful phenomena in all of astronomy: gravitational lensing. This is where the universe transforms itself into a cosmic telescope, where galaxies become magnifying glasses, and where light from the most distant corners of existence gets twisted, stretched, and multiplied in ways that reveal secrets hidden in darkness. Gravitational lensing is exactly what it sounds like. Massive objects bend passing light, acting as natural lenses scattered throughout the cosmos. But unlike the glass lenses in eyeglasses or telescopes, these cosmic lenses are made of curved space-time itself. A galaxy does not physically touch the light passing nearby. Instead, the galaxy warps space-time around it, and light follows that warped geometry. The result is that light from distant objects behind the galaxy gets deflected, focused, and distorted as it travels toward us. This bending follows precise mathematical rules determined by general relativity. The amount of bending depends on the mass of the lensing object and how close the light passes to it. The closer light travels to a massive object, the stronger the bend. A photon grazing the surface of our sun bends by a tiny angle, less than 2 seconds of arc. That is minuscule, but measurable, and exactly what Einstein predicted. A photon passing near a galaxy bends much more dramatically because galaxies contain hundreds of billions of stars worth of mass, plus vast amounts of gas, dust, and something else we will discuss soon. More mass equals stronger lensing. This relationship is direct and unavoidable. Double the mass and you roughly double the deflection angle, assuming everything else stays constant. A massive galaxy cluster, containing thousands of galaxies and all the matter between them, creates such powerful space-time curvature that light passing through can be bent by enormous angles, sometimes completely wrapping around the cluster. When we observe gravitational lensing, we are essentially watching light take detours through curved space-time. Imagine you are driving on a flat road heading due north. That is light traveling through flat space-time. Now imagine the road curves to the east. You still follow the road, but your direction changes. You end up somewhere different from where you would have gone on a straight path. This is light following curved space-time. The light itself does not know it is being deflected. From the photon's perspective, it is traveling the only path it can, the null geodesic through whatever space-time geometry exists. But here is where it gets truly remarkable. When the geometry is right, gravitational lensing can magnify distant objects, making them appear brighter and larger than they would otherwise. Think about using a magnifying glass to read small text. The glass bends light rays to make the text appear bigger. Gravitational lenses do the same thing, except they magnify entire galaxies. Distant galaxies that would be too faint for even our most powerful telescopes to detect become visible because a massive foreground object magnifies their light. Lensing can also distort shapes into arcs. We observe this constantly in deep images of galaxy clusters. Background galaxies that should appear as small, faint dots instead stretch into long, curved arcs wrapping around the cluster. These arcs are not physically curved galaxies. They are distorted images created by light traveling through severely curved space-time. The galaxy itself is still roughly circular or elliptical, but we see it smeared across the sky because different parts of the galaxy's light take slightly different paths through the curved space-time. Even more remarkably, gravitational lensing can duplicate images. The same galaxy can appear in multiple places in the sky simultaneously. How is this possible? Imagine light from a distant galaxy taking multiple curved paths through space-time, each path bending around different sides of a massive foreground object. Each path delivers light to our telescopes, creating separate images of the same source. Astronomers have found cases where a single distant quasar appears as 4 distinct points of light arranged around a foreground galaxy. This is called a quad lens, and it is direct visual proof that space-time really is curved. The most perfect manifestation of gravitational lensing happens when alignment is nearly exact. When a massive object sits almost directly between us and a distant light source, the bending becomes symmetric in all directions. Light curves around every side of the lensing mass equally, creating a ring of light in the sky. These are called Einstein rings, named after the man who first predicted their existence in general relativity. Einstein rings are hauntingly beautiful. They look like cosmic halos, perfect circles of light surrounding a central mass. They are rare because they require extremely precise alignment. The source, the lens, and the observer, that is us, must line up almost perfectly. Even a slight misalignment turns the ring into an arc. But when conditions are right, we see these luminous rings hanging in space, visual proof that light follows the geometry dictated by mass and energy. Gravitational lensing reveals invisible structures throughout the universe. This is not metaphorical, it is literal. When we observe lensing, we are mapping mass, not light. A galaxy could be completely dark, emitting no light whatsoever, and we could still detect it through its gravitational lensing signature. The bending of background light would reveal its presence like a fingerprint in space-time. This realization opened an entirely new way of studying the cosmos. For centuries, astronomy meant collecting light. We could only study objects that emitted or reflected electromagnetic radiation. Gravitational lensing changed that fundamentally. Now we can study mass directly, whether it emits light or not. We can weigh galaxies and galaxy clusters by measuring how much they bend light. We can map the distribution of matter on cosmic scales, creating three-dimensional maps of mass throughout billions of light years. And when astronomers started doing exactly that, mapping mass through gravitational lensing, they discovered something shocking. The amount of lensing they observed, the degree to which light was being bent, required far more mass than they could see. Galaxies were bending light as if they contained 5 to 10 times more mass than all their visible stars, gas, and dust combined. Galaxy clusters showed the same pattern, only more extreme. The visible matter, everything we could detect through telescopes, accounted for only a fraction of the mass needed to explain the observed lensing. Something invisible was out there, something massive, something that interacted with space-time through gravity, but apparently nothing else. This unseen mass was bending light, curving space-time, and shaping the evolution of cosmic structure. But it emitted no light, absorbed no light, and seemed to pass through normal matter like a ghost. Astronomers gave this mysterious substance a name that captures both our knowledge and our ignorance: dark matter. And gravitational lensing became the key to revealing where this dark matter hides and how it shapes everything we see. Gravitational lensing is not a single phenomenon, but rather a spectrum of effects that range from subtle distortions barely visible to the most powerful telescopes, to dramatic warping that transforms the appearance of entire regions of sky. Understanding this spectrum is crucial because different types of lensing reveal different aspects of cosmic structure. Astronomers divide gravitational lensing into two main categories based on the strength of the effect: strong lensing and weak lensing. Each tells us something unique about the universe, and together they form a complete picture of how mass shapes light across cosmic distances. Strong lensing occurs near extremely massive objects where space-time curvature becomes so severe that its effects are unmistakable. These are the showpieces of gravitational lensing, the images that appear in textbooks and science documentaries. Strong lensing produces the Einstein rings we discussed, the multiple images of single sources, and the dramatic arcs that stretch across the sky. When you see a photograph of a galaxy cluster with streaks and curves of light wrapped around it, you are looking at strong gravitational lensing in action. The most common locations for strong lensing are galaxy clusters, those enormous cosmic structures containing thousands of galaxies bound together by gravity. A typical galaxy cluster might contain 1,000 trillion times the mass of our Sun, concentrated in a region millions of light-years across. This immense mass creates profound space-time curvature. Light from galaxies billions of light-years behind the cluster must traverse this curved geometry, and the resulting deflections are massive. Strong lensing produces arcs, rings, and multiple images through geometric effects that are both beautiful and informative. When a background galaxy aligns well with a foreground cluster, but not quite perfectly, we see giant arcs. These luminous curves can stretch for hundreds of thousands of light-years across the sky. Yet, they are merely distorted images of galaxies that would otherwise appear as tiny dots. The galaxy itself has not stretched. Only its image has been transformed by the geometry of curved space-time. Multiple images appear when light from a single source takes several distinct paths around the lensing mass. Think of it like this. Imagine standing behind a thick glass sculpture with complex curves. Light from a candle on the far side might reach your eyes through multiple paths, each bending through different parts of the glass. You would see several images of the same candle. Gravitational lensing does exactly this with space-time itself, serving as the refracting medium. A single quasar might appear as 2, 4, or even more distinct points of light, each image showing the same object at slightly different times, because each light path has a different length. Perfect Einstein rings form when alignment is nearly exact, when the source, lens, and observer line up so precisely that symmetry dominates. The background source appears as a complete circle of light surrounding the lensing mass. These rings are rare treasures in astronomical surveys. They require not only excellent alignment, but also the right mass distribution in the lensing object. Too much mass clumping in one direction breaks the symmetry and turns the ring into arcs. Too little mass creates only subtle distortions. Strong lensing acts like a giant magnifying glass, but one with unusual properties. The magnification is not uniform across the image. Different parts of the background galaxy get magnified by different amounts, which is why we see such dramatic stretching and distortion. Some regions might be magnified 10 times, others 100 times. This variable magnification allows us to study distant galaxies in extraordinary detail, resolving features that would be completely impossible to see otherwise. Now contrast this with weak gravitational lensing, a far more subtle phenomenon that requires sophisticated statistical analysis to detect. Weak lensing happens with smaller masses, or when light passes farther from massive objects. The deflections are tiny, often less than 1% change in the apparent shape of a galaxy. You cannot look at a single galaxy image and say definitively that it has been weakly lensed. The distortion is too small, lost in the noise of intrinsic galaxy shapes and measurement uncertainties. But here is the clever insight. While individual galaxy distortions are undetectable, statistical patterns in thousands or millions of galaxies reveal the presence of weak lensing. Imagine you are trying to detect a gentle breeze. A single leaf might flutter randomly, and you cannot tell if wind moved it or something else. But if you watch 1,000 leaves and they all tend to flutter in the same direction, you know wind is blowing. Weak lensing works the same way. Astronomers measure the shapes of vast numbers of galaxies and look for correlated distortions that indicate spacetime curvature between us and those galaxies. Weak lensing causes subtle distortions, where images appear slightly stretched in particular directions. A circular galaxy might appear very slightly elliptical. An elliptical galaxy might have its axis rotated by a small angle. These effects are tiny, but they are real, and they carry information about all the mass between us and the source galaxy. This includes visible matter in galaxies, hot gas between galaxies, and crucially, dark matter. The effects of weak lensing require statistical analysis because we need to distinguish real lensing signal from random noise. Galaxies have intrinsic shapes that are not perfectly circular. Some are elliptical, others irregular. If we measure just one galaxy, we cannot tell if its shape comes from weak lensing or from how it formed. But galaxies are oriented randomly in space. Their intrinsic shapes point in random directions. Weak lensing, however, creates coherent patterns. It tends to stretch galaxy images tangentially around massive structures. When we average over many galaxies, the random intrinsic shapes average to 0, but the lensing signal remains. This statistical approach makes weak lensing incredibly useful for large-scale mapping of cosmic structure. Strong lensing tells us about individual massive objects, this galaxy cluster, that particular alignment. Weak lensing reveals the distribution of mass across enormous volumes of space. It maps not just clusters, but also the filaments connecting them, the voids between structures, and the overall geometry of matter distribution throughout billions of light years. Weak lensing is particularly useful for revealing hidden mass distribution, especially dark matter. Because the technique is sensitive to all mass, regardless of whether it emits light, weak lensing provides a complete census of matter. We can create maps showing where mass is concentrated and then compare these maps to where we see light from galaxies. The discrepancies reveal dark matter. Both strong and weak lensing operate on two cosmic scales, but they complement each other perfectly. Strong lensing probes the deepest space-time curvature around the most massive objects. It magnifies distant galaxies, allowing detailed study of the early universe. Weak lensing traces mass distribution across vast expanses, revealing the cosmic web of structure. Together, they transform gravitational lensing into one of the most powerful tools in modern cosmology, a way to weigh the universe and map its invisible skeleton. We have reached the moment where gravitational lensing transforms from an interesting optical effect into a revolutionary tool for unveiling the universe's greatest mystery. Everything we have built up to, the curvature of space-time, the bending of light, the magnification and distortion of distant galaxies, all of it converges on a single profound discovery. Most of the matter in the universe is invisible. We cannot see it with any telescope. It emits no light, absorbs no light, and reflects no light. Yet it is there, bending space-time, shaping galaxies, and determining the fate of cosmic structure. We call it dark matter, and gravitational lensing is the key that revealed its presence. The story begins with an uncomfortable observation. When astronomers mapped the distribution of mass in galaxy clusters, using gravitational lensing, they found something that defied explanation. The amount of lensing, the degree to which light was being bent, required enormous quantities of mass. But when they added up all the visible matter in those clusters, all the stars in all the galaxies, all the glowing gas between them, everything they could detect through telescopes, they came up drastically short. The visible matter could not explain the observed lensing, not even close. Visible matter cannot explain observed lensing. This is not a minor discrepancy that could be chalked up to measurement error. The gap is enormous and consistent. Every galaxy cluster studied through gravitational lensing shows the same pattern. The lensing signature indicates far more mass than we can see. In a typical galaxy cluster, visible matter accounts for only about 15 to 20% of the total mass needed to explain the gravitational lensing. The rest, more than 80%, is invisible. There is more gravity than visible mass. This realization did not come suddenly. Astronomers had suspected something was wrong for decades. In the 1930s, Fritz Zwicky studied the motion of galaxies within the Coma cluster and found they were moving too fast. The visible mass in the cluster could not generate enough gravity to hold those galaxies in orbit. They should have been flung apart long ago. Zwicky proposed the existence of dark matter, unseen mass, providing the additional gravity needed to bind the cluster together. In the 1970s, Vera Rubin studied rotation curves of spiral galaxies and found another anomaly. Stars at the outer edges of galaxies were orbiting just as fast as stars closer to the center. This made no sense according to visible matter distribution. As you move outward in a galaxy, visible stars and gas become sparse. Gravity should weaken and orbital speeds should drop. But they did not. Stars maintained high velocities far into the galactic outskirts, implying the presence of vast amounts of invisible mass extending well beyond the visible disk. These observations hinted at dark matter, but gravitational lensing proved it. Lensing does not depend on how matter moves or what assumptions we make about orbital dynamics. Lensing is a direct consequence of mass curving space-time according to general relativity. When we measure gravitational lensing, we are weighing the mass directly. The geometry of light paths tells us how much mass must be present, and the answer is always the same, much more than we can see. This unseen mass is called dark matter, a term that captures both what we know and what we do not. We know it exists because of its gravitational effects. We know it is matter in the sense that it has mass and curves space-time. But we call it dark because it does not interact with electromagnetic radiation. Dark matter does not emit light. It produces no photons through nuclear fusion, no thermal radiation from heat, no synchrotron emission from magnetic fields. It is electromagnetically invisible. Dark matter also does not absorb light. If dark matter clouds blocked light from background sources, we would see shadows, obscured regions in the sky. We do not. Light passes through dark matter as if it were not there, at least in terms of electromagnetic interaction. The only way dark matter affects light is through gravitational lensing, by curving the space-time through which light travels. Dark matter interacts through gravity and apparently nothing else. It does not participate in electromagnetic interactions. It does not seem to interact through the strong nuclear force that binds atomic nuclei together. Current evidence suggests it does not interact through the weak nuclear force either, or if it does, only extremely rarely. Gravity is the only force through which dark matter makes its presence known. This makes dark matter extraordinarily difficult to detect directly, but gravitational lensing gives us a way to map where it exists. Lensing maps dark matter distribution across the universe with stunning precision. By measuring how light from distant galaxies is distorted as it passes through foreground structures, astronomers create maps of mass. These maps do not show where light comes from. They show where mass exists. And when we compare mass maps to optical images showing where galaxies are, we see something remarkable. The mass distribution is much more extended and diffuse than the light distribution. Galaxies sit like bright islands within vast seas of dark matter. Galaxy clusters expose dark matter, halos, most dramatically. A typical galaxy cluster appears optically as a collection of galaxies scattered across a region of sky. But gravitational lensing reveals that those galaxies are embedded within an enormous dark matter halo, a roughly spherical distribution of invisible mass that extends far beyond the visible galaxies. This halo contains most of the cluster's mass. The galaxies themselves, with all their billions of stars, are merely minor components of the total mass budget. Light bends around invisible mass, creating lensing patterns that map dark matter with exquisite detail. Astronomers have created three-dimensional maps of dark matter distribution in galaxy clusters by analyzing lensing of background galaxies at different distances. These maps show that dark matter forms smooth, extended halos with galaxies embedded within them. The dark matter does not follow the galaxies exactly. It has its own distribution, shaped by gravity and the history of cosmic structure formation. Dark matter outweighs normal matter by an enormous factor. Current measurements indicate that dark matter comprises about 85% of all matter in the universe. Normal matter, the protons, neutrons, and electrons that make up atoms, stars, planets, and people, accounts for only 15%. For every kilogram of ordinary matter in the universe, there are roughly 5 to 6 kilograms of dark matter. This is not a minor correction to our understanding. This means most of the matter in the universe is fundamentally different from everything we have ever touched, seen, or studied in laboratories. About 5 times more dark matter exists than ordinary matter. This ratio has profound implications. It means the universe is not primarily made of what we are made of. The atoms in our bodies, built from protons and neutrons forged in the Big Bang and inside stars, represent a minority component of cosmic matter. The majority is something else entirely, something that clumps under gravity but otherwise seems ghost-like in its interactions. Dark matter shapes galaxy formation and cosmic evolution. Computer simulations of structure formation show that without dark matter, galaxies as we observe them could not have formed. The universe expanded too fast after the Big Bang. Ordinary matter alone could not clump together quickly enough to form the first galaxies before expansion diluted everything. Dark matter provided the gravitational scaffolding. It clumped first, creating potential wells that attracted ordinary matter. Gas fell into these dark matter halos, collapsed, and formed stars. Galaxies, as we know them, are built on foundations of dark matter. Gravity gives away what eyes cannot see. This is the profound lesson of gravitational lensing and dark matter. For centuries, astronomy meant looking at light. We could only study objects that shone or reflected light. Gravitational lensing changed this forever. Now we study mass directly through its geometric effects on space-time. We map the invisible, we weigh what cannot be seen, and in doing so, we discovered that the universe is far stranger and more mysterious than anyone imagined. Most of what exists is hidden, revealed only through the bending of light around cosmic structures we can never directly observe. We have journeyed from the fundamental nature of gravity as curved space-time, through the bending of light despite its lack of mass, into the phenomenon of gravitational lensing, and finally to the revelation of dark matter dominating the cosmic mass budget. Now we arrive at the practical question: how do we actually use gravitational lensing to study the universe? What tools allow us to map invisible matter across billions of light years? The answer lies in space telescopes specifically designed to exploit lensing, instruments that transform the universe itself into a laboratory for studying its hidden architecture. The story of mapping dark matter through gravitational lensing begins in earnest with the Hubble Space Telescope. Launched in 1990, Hubble revolutionized astronomy by providing unprecedented views of the cosmos from above Earth's distorting atmosphere. Among its many contributions, Hubble became the premier instrument for studying strong gravitational lensing in galaxy clusters. The telescope's sharp vision allowed astronomers to identify and analyze the dramatic arcs, rings, and multiple images created when light from distant galaxies passes through massive foreground clusters. Hubble Space Telescope uses strong lensing to peer deeper into cosmic history than would otherwise be possible. When Hubble images a galaxy cluster, it captures not just the cluster itself, but also the distorted images of hundreds of background galaxies lensed by the cluster's gravity. Each arc, each stretched image, contains information about both the lensing mass and the lensed source. By carefully modeling how light has been deflected, astronomers can reconstruct both the mass distribution in the foreground cluster and the properties of the background galaxies. Hubble revealed dark matter structures with stunning clarity. One of the telescope's most famous contributions is the creation of detailed dark matter maps for individual galaxy clusters. Astronomers analyze the positions and shapes of lensed background galaxies, measuring how much each image has been distorted. This distortion pattern directly reflects the mass distribution in the cluster. By combining measurements from dozens or hundreds of lensed galaxies, they build up a complete picture of where mass exists, both visible and dark. Lensed galaxies appear smeared and arced in Hubble images, their light stretched by the curved space-time geometry they traversed. Some of these arcs are so distorted they wrap halfway around the lensing cluster. Others appear as thin streaks of light, single galaxies stretched into curves spanning hundreds of thousands of light-years in apparent size. These distortions are not just beautiful, they are data. Each curve encodes information about the mass that deflected it. Mass maps exceed visible matter dramatically in every case Hubble studied. When astronomers create mass maps from gravitational lensing and overlay them on optical images showing where galaxies are, the discrepancy is obvious. The mass distribution is much broader and more extended than the light distribution. Peaks in the mass map do coincide with concentrations of galaxies, but the mass extends far beyond the galaxies themselves. These maps provide direct visual evidence that most matter in galaxy clusters is invisible. This confirms dark matter dominance conclusively. Gravitational lensing gives us a technique that is nearly assumption-free. We are not relying on complicated models of galaxy dynamics or gas physics. We are simply measuring how much mass is present based on how much it curves space-time, and the answer is always the same: far more mass than we can see. The evidence from Hubble's gravitational lensing studies, combined with many other independent lines of evidence, leaves no reasonable doubt that dark matter exists and dominates the matter content of the universe. But as powerful as Hubble has been, it has limitations. Hubble's field of view is relatively small, about the size of a grain of sand held at arm's length. This makes Hubble excellent for detailed studies of individual objects, but inefficient for surveying large areas of sky. Strong lensing requires finding rare, well-aligned systems. Weak lensing requires measuring shapes of millions of galaxies spread across huge areas. Hubble simply cannot cover enough sky fast enough to map cosmic structure on the largest scales. This is where the Nancy Grace Roman Space Telescope enters the story. Currently scheduled to launch in the middle of this decade, Roman is designed specifically to address Hubble's limitations, while pushing gravitational lensing studies to entirely new levels. Roman will be optimized for wide-field surveys, capable of imaging areas of sky 100 times larger than Hubble can capture in a single exposure. This enormous field of view transforms what is possible with weak gravitational lensing. Nancy Grace Roman Space Telescope will advance this work beyond anything previously possible. Roman focuses on weak lensing as one of its primary science goals. The telescope will conduct surveys measuring the shapes of hundreds of millions of galaxies across large fractions of the sky. This enormous statistical sample will allow astronomers to map dark matter distribution throughout the observable universe with unprecedented precision. Roman focuses on weak lensing because weak lensing traces mass on the largest cosmic scales. While strong lensing reveals individual massive clusters, weak lensing maps the entire cosmic web, the filaments of dark matter connecting clusters, the distribution of matter in less dense regions, and the overall geometry of cosmic structure. Roman will create three-dimensional maps of dark matter extending billions of light-years in depth, showing how dark matter has evolved over cosmic history. It detects smaller dark matter clumps that were beyond Hubble's reach. Weak lensing signals from less massive structures are subtle and require measuring many galaxies to achieve statistical significance. Roman's wide field of view and efficient survey speed mean it can measure enough galaxies to detect dark matter concentrations much smaller than galaxy clusters. This will test theories of dark matter by revealing how it clumps on different scales. Roman's field of view vastly exceeds Hubble's, covering an area equivalent to 100 Hubble fields in a single image. This might not sound revolutionary, but it changes everything for survey efficiency. Where Hubble would need hundreds of separate pointings to cover a region of sky, Roman captures it all at once. For weak lensing surveys that need to measure millions of galaxies, this efficiency is transformative. Data collection will be exponentially faster with Roman than was ever possible with Hubble. Roman will measure more galaxy shapes in its first year of weak lensing surveys than Hubble measured in 3 decades. This flood of data will feed into sophisticated analyses that map dark matter distribution, measure the expansion history of the universe, test theories of gravity on cosmic scales, and reveal how structure has grown over billions of years. Roman will map cosmic evolution by observing how dark matter distribution has changed over time. Because light from distant objects took billions of years to reach us, looking deeper into space means looking back in time. Roman will measure weak lensing at multiple cosmic epochs, creating snapshots of dark matter distribution at different times in cosmic history. By comparing these snapshots, astronomers will watch how structure has grown and evolved, testing our understanding of cosmic expansion and the influence of dark energy. Lensing lets us see the universe's skeleton, the underlying framework of dark matter on which all visible structure hangs. Galaxies are not randomly scattered through space. They follow the distribution of dark matter, forming along filaments and clustering at intersections in the cosmic web. Gravitational lensing reveals this web directly. It shows us the architecture that gravity has constructed over billions of years. This is the culmination of our journey. We started with gravity as curved spacetime, not a pulling force. We explored how light bends despite having no mass because it follows geometric paths through curved space. We discovered gravitational lensing, both strong and weak, as natural cosmic telescopes that magnify and distort light from distant sources. We found that lensing reveals dark matter, the invisible substance that comprises most of the universe's mass. And now we see how space telescopes like Hubble and Roman transform lensing into a practical tool for mapping cosmic structure on the grandest scales. The universe has handed us a gift. Gravitational lensing allows us to see what cannot be seen, to weigh what cannot be touched, to map the invisible foundations on which everything visible is built. As we look toward the future with missions like Roman, we stand on the threshold of understanding the universe's structure in ways that would have seemed like magic just decades ago. Light, bent by gravity, reveals secrets hidden in darkness.